stop. E2. Is that right, Mike?
Yeah.
E2. Did I talk about the transition state? E2.
Yeah.
That's what let's go with the E2 transition state, E1, then we'll work some examples. Let me, oh, all right. Hopefully everybody had a great homecoming. I did. I enjoyed it. I know this is kind of like getting back on a bicycle after this weekend, but got to get back on it. So we're going to start out with the E2. Last time we talked about E2, we talked about the mechanism, and also we talked about the rate law, if I'm not mistaken, or the go back, make sure I don't. Yes, we did. We talked about the rate law, we talked about the mechanism. There's only one other thing I want to talk about with the E2, and that's the transition state and the geometric requirement for E2. So let's talk about that. I think we were down here working on some E2 examples. All right, so all right, so we're going to talk about this geometric requirement for the E2 as well as what the transition state looks like. And before we go any further, can y'all hear me okay? The 11 of you who are logged in?
Yes.
Okay, cool. If anytime the sound goes out, just unmute and say something. All right.
You get absolutely covered in chocolate, marshmallow, and a little bit of crumbs of biscuit. I think it's all right. But hold back. Got another set to try then.
All right, so let's talk first about the transition state. I'm going to steal image.
It's also something that holds together and listens to carefully so that when I roll it out, it'll still hold you. Hello.
Hello.
Did you get a handshake?
Hey,
I did. Right hand.
Can I
I haven't
touch
watched it since then.
Can I touch it? I need some of that power.
That full power.
Feel like.
Oh, surprise.
Yeah, feel like. Show me that.
all right. Let me take this image. And we're going to use that to talk about the transition state. So you can see based on the image here, which bonds are being broken, which bonds are being made. And so that is the knowing where the arrows are and what bonds we're making and breaking is going to help us define what the transition state looks like. Right? Some of that, I'll give you time to write that down because I realized that I cheated. I stealing it from another part of the page. But what can you say about the arrows here? What's happening here? Anybody? You remember the, let me put this up. Radius K times the substrate concentration times the base concentration. So look at the arrows. Tell me what I'm doing with that one I have highlighted in green. What is that arrow indicative of? Okay, so the oxygen is making a bond with hydrogen. Good. What about this arrow? What does that mean? Y'all see that? I'm talking. What does that mean? If I draw an arrow from that CH bond and put it there between these two carbons, what does that mean? Pi bond, that's what my pi bond. We're doing an elimination, that's what my pi bond is going. What about this? What does that mean? So the Ci bond is breaking, and I know the electrons are leaving without that. So here we can say that I'm forming an HO bond, right? And then CC pi bond is forming. And then Ci is breaking. Right, so over C, and then we also are breaking the CH bond right here. Right, that's what our transition state must indicate. It has to look like these things are happening. Right, so let me copy that again. Show you this one. Arrows out. And we're going to replace those bonds with dotted lines, just like we've done before. So you have this bond forming, this bond breaking, this bond forming, and then that bond breaking. Right. So that's what the transition state is going to look like. Partially broken bond between C and H, partially formed bond between carbon and carbon, partially broken bond between C and I, and then partially formed bond between O and H. So I want to put this in bracket. Double that. So this is my transition state. All right, I'll give you time to get that down. I stole that. But this is why this second order overall. The OH right here is involved. This is your base. The rest of it is substrate. All right, so that's why it's second order overall. That's why we call it bimolecular. That's why we call it E2. right? All right, any questions about that? About the transition state? That's one other thing I have to talk about with the E2. And that is the geometry of, and we can see it from the transition state, right? So for the E2, you can notice that the hydrogen here that's being removed and the iodide here are opposite to one another, right? They're on opposite sides of the same plane, right? So the alpha hydrogen and the leaving group have to have a specific geometric relationship. We call it anti, or the alpha hydrogen. And the leaving group must be what we call anti-periplane. Right? That means is that they have to be on opposite sides of the same plane. They have to be opposite to one another. So you couldn't eliminate if the I and the H were on the same face, like right adjacent to one another. All right, and I'm gonna show you what that means in terms of what we call a Newman projection too in a second. But that geometry is required. For E2, if your leaving group of your alpha proton can't be anti-periplanar, it won't eliminate. All right, any questions about that part? Let me show you something real quick. We're gonna study Newman projections later, but I'm gonna introduce you to it now, just so you can see what I mean. So if I have a, so we're gonna look at what's called a Newman projection. So if I have two carbons that look like this, right, over on CH3, right? If I wrote those out like this and show the geometry of the carbon, which is tetrahedral, we learned that way back in August. All right, I can depict this carbon-carbon bond as what we call a Newman projection. And what I would basically be doing is looking, excuse me, looking down the bond right here. This is my eye, and I'm looking down the bond. My eyes look crazy at the moment. So I'm looking down that bond. If I do that, I'm going to see, I should have brought my models to class, but the back carbon, we're going to call this back. And this carbon, so the back carbon is the big circle, that's the one I like the same color, so that's this one. And then the front carbon, I'm just going to represent as a dot. Right, that's this one. Red and like that. All right. So on each carbon, on the red carbon, I have 3 hydrogens. Is that right? And so on the green one, I have 3 hydrogens. So I'll put those in, and they can, I'm going to put them in static first, and then I'll explain what that means. So I have a hydrogen here, here, and here, based on the geometry. So that's H, H. Right, and then on the front carbon, I'm going to put my hydrogen in like this. This is what we call a Newman projection. Newman projection. Like you look down the carbon-carbon bond, and it doesn't matter how long the chain is, the Newman projection is only going to represent 2 carbons out of that chain, no matter which 2 carbons you pick. It's inconsequential. So this confirmation of a Newman is what we call staggered. It's called staggered. The angle between each hydrogen is 60 degrees. It's what we call a dihedral angle. $60-degree dihedral angle. $60-degree dihedral angle. So in the staggered conformation, all the angles between all the hydrogens are 60 degrees. Right? I can take this, wish I should have brought my models. I can take it and rotate it so that all the hydrogens overlap. So that'll give me another conformation. So let's draw that. That conformation is going to be what we call the eclipse conformation. I'll fix this when I'm so far. Let's do that. So let's take that. Like the other one. And I'm going to leave the back part of how it was. Right now, all your hydrogens are overlapping. What I did was rotate around the carbon-carbon bond. Right, so I rotate around that bond and close that, compress those dihedral angles. So now over here, this is what we call eclipse. The eclipse confirmation. Got staggered and eclipse. And those, because you can rotate around the carbon-carbon bond, those conformations are basically oscillating between one another. But the eclipse is much higher in energy. Right, and the dihedral angle between the hydrogens here is now 0. And it costs energy for those hydrogens to overlap. I think for a hydrogen is like 4 kilojoules per mole or something like that. But that's not what I want to talk about. All right, questions? Any questions about that? About the angle, about the projection? Again, what I'm looking at is I'm taking that those 2 carbons that I have highlighted, red and green, and I'm looking down the bone. It's almost like if you were looking at a car from the side, like the front tire, and then you're looking at the front tire from the side and the other tires behind it on the other part of the axle. That's exactly what's happening here. All right, what I want to define here is what I mean by anti. Right? So in the staggered conformation, this hydrogen right here all right. So these 2 hydrogens right here are what we call anti. One at the very top and the one at the very bottom. in the staggered conformation. We call that positioning anti, meaning they are 180 degrees apart. Right? So when we say anti or anti-periplanar, that's what we mean. The two groups have to be 180 degrees apart from one another. Right? Any questions about the anti part? I'll clean this up before I post it too. All right, so if we go back over here and just look at these two carbons where the elimination is taking place, right? So we can draw, let's make them. So I'm gonna make that one the back carbon. So we can draw that. This is the back carbon where the two hydrogens are going to be. We're going to put those, I'm going to keep them red too. One is going to be here. One here. And over here, you have another group. That's this group right here. Right, and then on the bottom, on the other carbon that's in green, where the iodine is, I'm going to make that the front carbon. So your iodide is here. And then you have a hydrogen here and another carbon. That's just solid. That's for right. But the point is, this is what I'm trying to get at. That this hydrogen, the one that's getting pulled off, and this iodine have to be in this anti position. Like the iodine has to be 180 degrees away from that hydrogen. And that's one of your alpha hydrogens. This is required. Again, E2 cannot happen unless your alpha hydrogen and your leaving group are anti to one another. And that's what that means. Anti-periplanar. Opposite sides of the same plane. Right? Any questions about anything? All right. So between that and the transition state, that's all I wanted to touch on with E2. We're going to do E1. And then work through some examples probably on Wednesday, and then be done with this on Friday or by Friday. All right. Any questions? We did, didn't we? Yeah, we did it right here. Okay, never mind. We're gonna do some examples. Take 749. Actually, no. Hold up. All right, it just said, all it asks us is to draw the product. Let's do that. All right, let's take A, and these are all substitutions, by the way. I'm gonna add another layer in and ask what type. Maybe I'll add a solvent or something of that nature, so we can kind of identify. Type. All right, so let's do A. Right, what would the product be from that? So what we need to do is identify substrate, nucleophile, and let's say that this is done in ethanol. So let's identify substrate, nucleophile. I'm giving you the solvent, so we're going to determine if that's protic or aprotic. And then we'll write the product. So your substrate, is it, how do we identify, how do we classify it? Is it primary? Is it secondary? Is it tertiary? And where's my leaving group? Anybody? Where's the leaving group on here? The chlorine. Good. So this is my, I've identified my leaving group. It's a very good leaving group. If you go back and look at that list. All right, and then so my substrate is what? Is this secondary? Is that a secondary carbon? What a chlorine is? So here's the carbon that I'm looking at. How many carbons are attached to it? So it will be secondary, right? So remember we talked about secondary carbons being able to do both SN, because these are all substitutions, SN2 and SN1 substitution. All right, so if I do it in ethanol, is ethanol protic or aprotic? Protic, good. Protic solvents facilitate which type of substitution? SN2 or SN1? Answer that, then we'll know the mechanism. SN1. So the fact that this is a secondary carbon, they can do both. Right, the difference usually comes down to the solvent, whether it's protic or aprotic. If it's a protic solvent, then more than likely it's going to be an SN1. If it's an aprotic solvent, it's going to be SN2. And then this is my nucleophile. And I'm going to put some electrons here on oxygen. Right? That's the part of the nucleophile that's going to react. And we know it's SN1. So what's the product look like? If it's the oxygen in the nucleophile that's reacting, what would the product look like? And let me ask this question: Do y'all need to see the arrows for the mechanism? Because we could do that too. Okay, I see one head nodding. Any two heads? No. Yeah. Okay. Let's do that. If it's SN1, what's the first step? For SN1, first step is always what? The rate. What's the rate determining step? for SM1. Well, sometimes it may not be the first step, but it's the main thing that has to happen. How do you get to the carbocation intermediate in the SM1? What do you have to lose? I lose leaving group. So that's here. It's a good leaving group, so we can just show that part. So we lose our leaving group and we get to this intermediate. That's positive, and then fluorines out here hanging out. Like so, right? And then the nucleophile is going to attack. So this is my nucleophile. Right, that's coming in, and that's going to attack, boom, right here. And then that's going to give me a product where now I have a bond between carbon, that carbon that's positive, and the oxygen that's negative. Questions about that part? That's my product. So it's that plus chlorine, of course. That's not going anywhere. Any questions about that? Anybody not see how we got there? Right, let's do another one. Let's do, I'm gonna swap out D, but D is also gonna be tested. All right, let's take D. All right, where is in B? Where's my leaving group and where's my nucleophile? Because keep in mind, whenever you're doing a substitution, those are the two things that are changing places. Right? That's what's being substituted. The leaving group is being substituted by the nucleophile. So this is my substrate here. That makes this my nucleophile. But the sodium, sodium is +1, so it's not negative. And the cyanide is negative. So that's that CN functional group. That's what it looks like. A carbon with a triple bond to nitrogen. It's a cyanide or a nitrile. We call it a nitrile too. But when it's negative like that, we call it a cyanide. All right, so we know what our nucleophile is, and this is the part that's reacting through carbon, by the way, not nitrogen, because carbon is negative. And negatively charged nucleophiles are better than neutral nucleophiles. All right, so that's that. And then this is my substrate. I see my leaving group iodine. So what is the product of this reaction? In a substitution, my nucleophile replaces my leaving group. What's the product? Don't worry about sodium. Only focus on the cyanide. Anybody? I know it's Monday after homecoming. I'm asking too many questions. Would it be this? Is that right? Didn't we do this example when we were talking about the mechanism, when we were going through the mechanism and pushing arrows? I think we did. Or we did something close to it. Questions about that? All right, let's do C. We're gonna actually go through the mechanism to C, and then I'm, write the products out first. Right, what, in this case, what do you think the, water is gonna be? Nucleophile or substrate? What is my nucleophile? Water is really interesting. It can be a nucleophile or it can be an acid, which is somewhat of an electrophile, or it can be a base. All right, so here, water is my nucleophile. That makes this my substrate by default. And iodine is my leaving group. What do you think? This is a tertiary carbon. Can it do SN2? Tertiary carbon. Is it possible to do SN2 on a tertiary carbon? Good. Oh, you say yes? Get out. I'm just joking. I'm joking. You cannot do a SN2 on a tertiary carbon. Didn't I use you as an example when I put all them chairs in front of you? You forgot. I know it's on homecoming was Friday. It's okay. But SN2 is strictly for primary, secondary. Tertiary is always SN1. All right, so the first step here is going to be what? In this reaction, what's the first step? I'm getting some telepathic waves coming through Zoom. Somebody said in their mind that you lose your leaving group. Hopefully, that's what you're saying in your mind. Now you get this tertiary cation plus ions plus H2O. All right, and then it's the water that's going to attack that plus charge, like so. Right? That will not stay that way. The water protonated like that, that's not going to stay that way. I want that to become an alcohol. Do I have anything present that can help me with that? If I wanted to do, if I wanted to get rid of one of those protons, what would I do? Well, what could I do? Something we talked about a bunch, especially when we were studying pKa. Can I do a proton transfer between the hydrogen and iodine? Can I do this? That'll give me this alcohol here. Plus H I. All right. Any questions about any of the examples we looked at? If not, I'm gonna give y'all 2 free minutes. That's a lot of time in teaching time. Any questions from anybody that's logged in? I lost 2 people already. All right, if not, we're gonna pick up on Wednesday with, I want to do a couple of elimination examples, and then we'll be done with this section. We're gonna move on to another section. All right, any questions? All right, y'all have a great day.
Thank you. Have a good day.
All right.
You too.